let's get started here with section 3.3, properties of functions, and a few objectives to go through here. The first one is determining whether your function is even or odd by looking at the graph. So here's the definition. A function is even if for every number x in its domain, the number negative x is also in the domain. So let's think about what that means. If you plug in x and plug in negative x, you get the exact same thing. So x and negative x get you the exact same y value. Alright, so x comma y and negative x comma y will be on the graph, right? You plug in x, you get y. You plug in negative x, you get y. You're odd if you plug in negative x and you get the opposite y. So if you plug in x and you have y, you plug in negative x, you get negative y. So you get the opposite points. So let's go ahead and take a look at the theorem here. A function is even if and only if its graph is symmetric with respect to the y-axis. So we're even if we are symmetric with the y-axis, and we are odd if we're symmetric with respect to the origin. So let's take a look at the graph here. This graph is symmetric to the y-axis, so this is going to be even. And you'll notice here if we had a, let's take this point here, that x matches up with this y value up here. If we went to the negative, same distance from the y-axis, we'd have the same y value. So that's going to be even and symmetric to the y. This middle graph here is neither even nor odd. It's not symmetric with respect to the y or to the origin. And this one here is symmetric with respect to the origin. Everything that's happening in quadrant 1 is mirrored in quadrant 3. So this graph is going to be odd. All right, now that we know that, see if you can do problems 21a, b, and d. Second objective, let's see if we can tell whether functions are even or odd just from looking at the equation. So here's our first equation. Oh, that was the third one. There we go. Here's our first equation. Negative 3x to the fourth minus x squared plus 2. Okay, so for every x that we see, we're going to plug in a negative x and see what happens. So negative 3 negative x to the fourth minus negative x squared plus 2. And negative 3, a negative to the fourth is just going to turn right back into x to the fourth, minus negative x squared just turns back into x squared, and plus 2, nothing happens there. So this, we get the exact same thing as when we started. So f of negative x, when we plugged in negative x, we get the same thing as if we just plugged in x. So this is an even function. Let's check out the next one here. 5, we'll plug in negative x cubed, minus 1. That's equal to negative 5x cubed, because a negative cube stays negative, minus 1. So this is not equal to what we started with because of the negative out front, right? But, so it's definitely not even. The test is if we divide by a negative 1 and get the same thing, then we're odd. Let's see what happens. So negative 5x cubed divided by negative 1 is going to be 5x cubed. All right, here we're back to where we started. But negative 1 divided by negative 1 is plus 1, not what we started with. So this is neither. Okay, no symmetry. It's neither even nor odd. Let's test the last one here. 2 negative x cubed minus negative x. We'll simplify and have negative 2x cubed plus x. If we divide the whole thing by negative 1, we get 2x cubed minus 1, which is exactly what we started with. I'm sorry, minus x, right? X divided by negative 1. And that is what we started with. And so this function here is odd. All right, try problem 33. Objective number 3, let's determine when a graph is increasing, decreasing, or constant. So if we have a graph that looks like this, when is it increasing? It's increasing, you can see here from the red, between the x values of negative 4, and it's increasing, getting higher, the y values are increasing until it hits 0, 4. So it's increasing until it hits 0 in the x dimension. Right? So we want to say what x values are our y values going up. So these numbers here are going to be the x values that we're pulling off here, the negative 4 and the 0. All right, when is it decreasing? There's one section. So this is going to be decreasing from -6 to -4. And notice how we've used the parentheses and not the brackets, because it's not decreasing at this point. It's decreasing as soon as we leave that point. If we're at that point, we're standing still. Where else are we decreasing? There's the other spot. We're decreasing from 3 to 6, the x values again. The y values are going down when the x values are going from 3 to 6. All right, last one. When is the function constant? Right there. So that's going to be from an x value of 0 to an x value of 3. And then every part of the graph is taken care of. All right, so here's the definitions that we just talked about. You can pause it and get those down if you choose, if you haven't already gotten a good definition for increasing, decreasing, and constant of a function. Okay, so here's another example. We're increasing here. We are decreasing the whole time. Even though it's not decreasing the same amount, it's still going down the whole time. Here we're constant the whole time. 11, 13, 15, and 21C are yours to try. Okay, let's try to find the local maxima and local minima of graphs. So a local maxima is the point that's the highest point within some little region. Now this isn't to say that somewhere else we have a higher point. That's fine. We're just saying within a particular region, it's the highest point we can find. Same thing for a local minima, all right? It occurs at x equals c, so we're just saying the minima occurs there, and it has a value of this. So remember when we talked about local minimum and maximums before, remember that it occurs at x with a value of y. All right, don't get those confused. So there's that definition again. Let's see if we can figure it out here. So at what numbers, if any, does f have a local maximum? So there's only one point here. That's the top of a mountain, and it's right there. We don't consider the arrows here to be maxima because there's no point where it turns over and goes back downhill. All right, so only when we have an increase to a decrease like this, a top of a peak or a mountain, however you want to think about it. So at what numbers does it have the local maximum? It's happening at 1. And what is that local maximum? It's 2, right? X value, Y value. All right, how about minimum? So at what numbers do we have one? There's one. So at -1 and at, right here, this is 3, 0. So at 3, and the minima are, the Y values, 1, and the Y value here would be 0. All right. Let's list the intervals on which f is increasing. F is increasing from here to here. So we're increasing. F is increasing from -1 to 1. And it's also increasing here, this way, from 3 to infinity. It's decreasing from -infinity all the way over here, all the way down to a x value of -1, so -infinity to -1, and it's also decreasing from 1 to 3. And there we go, we have all the intervals. So try that with problems 17 and 19. Okay, so let's use a graphing utility now to approximate the local maxima and minima and to see when we're increasing and decreasing. So here's our function. I'm going to go over to our graphing calculator. Where are you? There you go. And plug this in. So y equals 2x cubed minus 3x and plus 1. Okay, and we also here have some restrictions. So we only want to graph this from -2 to 2. So we can actually tell our graphing calculator to do that. The way you do it, I'm going to back up here. You put your equation in parentheses. So second insert here, so I can insert a parentheses. And I'll go to the end and insert a parentheses there. All right, now it does not allow for compound inequalities, at least the version I've got here. If you have a more advanced version, it might. But you have to put this in as 2. -2 is less than x. We're going to put that in parentheses. We're going to say -2. The less than, I think we've seen this before, is in test here. Second test right there. negative 2 is less than, number 5, x. We also, I'm going to close my parentheses. We also want to say x is less than 2. We have to do that separately, at least on this version. So x is less than 2. All right, so we have the compound inequality here. Negative 2 is less than x, and x is less than 2. Two separate parentheses. I go ahead and graph that, and it's only going to graph from negative 2 to 2. Now, kind of hard to see here. Let me change my window here. So it's negative 3 to 3, and how about negative 20 to 20, and we'll get a better picture of this. You can see here it's not going to graph to the left of negative 2. It's not going to graph to the right of positive 2. All right, so now back to the question at hand. What are the local maxima and minima? So the local maximum is right here. Let's calculate it. Second, calculate a maximum. And it's the same thing we've done before. We need a left bound, so we need to be to the left of the maximum. We need a right bound. Hit enter there. And we need a best guess. That's pretty good. All right, so we have a maximum at negative 0.71 if we were rounding to 2, and y equals 2.41. We'll do the same thing for a minimum. Second, calculate a minimum, number 3. Left bound to the left of the minimum. I'll hit enter there. Again, you just need to approximate. It doesn't need to be precise here. Right bound, and there's our best guess. And so the minimum occurs at 0.71 and y negative 0.41. All right, so try problem 45. Out of the way, there we go. All right, so let's find the average rate of change of a function. So the average rate of change is the exact same thing as slope. So y1, right, f stands for y, y1 minus y2 over x1 minus x2. Those are the same things here, right? The x that goes with this y and the x that goes with this y. Now, we are going to do this. The reason we say rate of change instead of slope is because we're going to do this on functions that aren't straight lines. But we're going to create a line that connects 2 points. So, jumping ahead a little there, let's go back to this and find the average rate of change for this function. F of x equals 1/2 x squared from 0 to 1. All right, so 1/2 x squared, I'm going to plug in a 0. 1/2 0 squared obviously is just 0. So I'm going to say 0 minus, let's plug in 1. 1/2 1 squared, and so that's 1 squared is 1 minus a half. And so let's plug in the x values that got those 0 minus 1, right? These are the y values up here, and these are the x values down here. Simplify, this is negative half over negative 1, which is 1/2. That's our average rate of change from 0 to 1. Let's try 0 to 3. All right, we already have 0. Let's plug in 3. 1/2 3 squared is 4.5. So 0 minus 4.5 over, and we plugged in an x of 0 minus 3. So we have 4.5 over 3, which would be, if we doubled both of those, 9 over 6, which is 3/2. And last one, 0 to 5. Let's plug in 5. 1/2 of 5 squared. So that's going to be, let's use some fractions here. This is going to be 0 minus 25 over 2, all over 0 minus 5. So now we've got 25 over 2, all over 5. Never divide fractions. Let's go multiply the reciprocal. 25 over 2 times 1 over 5. And we can do some canceling. We'll be left with a 5 there. And so we'll have 5/2 here. All right, problem 53, yours to try. So, we have the rate of change is the slope of this line. The line itself is called the secant line. So, we can calculate that for any equation. So, we're going to do this from the points negative 2 to 1 for this function. Negative 2x squared plus 4x minus 3. So, let's start by finding the average rate of change. Plug in negative 2. negative 2 squared, plus 4 times negative 2, minus 3. And so what do we have here? Negative 2 times 4, minus 8, minus 3. And so that's negative 8 minus 8 is negative 16, minus 3 is negative 19. And so that'll go on top. Minus, what happens if we plug in a 1? We'll do that over here. Negative 2, 1 squared, plus 4 times 1, minus 3. So this is negative 2 plus 4, which is 2, minus 3, and we get negative 1. So minus negative 1. And let's subtract the x's. So we have negative 2 minus, positive 1. So negative 2 minus 1. And so we have negative 18 over negative 3. And so we have an average rate of change of 6. All right, so now what are we going to do with that? Let's find the equation of the secant line from here to here. And the way we're going to do that is with our old friend, the point slope, y minus y1 equals m, which we have right here. That's the average rate of change, x minus x1. All right, so we have two y values, and that's going to be, we can pick either one. Let's go with these values here. They're a little easier to use. So y plus 1 equals 6, x minus 1. And so we could leave it like that if we want a point slope. If we wanted slope intercept, we could clean it up. Y plus 1 equals 6x minus 6. So y equals, we minus the 1 to both sides, 6x minus 7. And let's use the graphing utility, draw the graph of g and the secant line obtained in part B on the same screen. Okay, so here we go. Let's go back to our graphing calculator. There we are. Get rid of u. Y equals, let's clear u out and plug both things in here. So negative 2 x cubed plus 4x minus 3, and then we'll go ahead and also graph 6x minus 7, and we'll graph it. And we're going from negative 2 to 1. So from negative 2 to 1, let's see here. Change our window a little bit. Let's go back to our standard. Hold on one second. All right, there we go. Sorry, I had to check in here. I put a cube there instead of a squared. So when we graph this, you'll see at negative 2, we're touching there, and at positive 1, we're touching there, we're intersecting, and you've drawn your secant line. All right, so that's it. Any questions on this? We'll go over them all in class. Good luck with those problems.